Angle of depression, introduction. Welcome, everyone. Today, we are going to begin a new topic in our study of trigonometry. As we move forward into the study of heights and distances, you will notice that we often encounter real-world scenarios where an observer is positioned at a significant height, perhaps standing on a balcony, a cliff, or a tower, and is looking down at an object located on the ground. Now, while we can see this happening with our eyes, in mathematics, we need a way to measure exactly how much that observer is looking downwards. To quantify this specific observation mathematically, we use a concept known as the angle of depression. Over the next few slides, I will show you exactly how to identify and calculate this angle. Understanding the concept. If you look at the screen, you'll see the formal definition. The angle of depression is the angle formed between the observer's horizontal line of our sight and the actual line of sight when the object being viewed is located below the observer's eye level. I know that sounds a bit wordy, so let's break this process down into 3 small, manageable steps to make it much clearer. First, let's consider the horizontal level. I want you to imagine an observer standing up on a high platform, perhaps a balcony or a tall tower. Before they even notice the object on the ground, imagine them looking straight ahead, perfectly level with the horizon. This imaginary straight line, extending from their eyes straight forward, is what we call the horizontal line. Second, we have the line of sight. Now, imagine the observer lowers their head to look down at the object on the ground. The imaginary line that connects the observer's eye directly to that object is called the line of sight. Finally, we arrive at the angle. The angle created between that original horizontal line, where they were looking straight ahead, and this new line of sight, where they are looking down, is exactly what we define as the angle of depression. Now that we've introduced the basic idea of looking down from a height, let's dive deeper into what this angle actually represents. Keep this mental image in mind, because in the next slide, we are going to see how this angle relates beautifully to the angle of elevation using some geometry principles. The geometric relationship. Now that we understand what the angle of depression actually is, let's look at a critical point that will make solving these problems much easier. When you are working on problems involving heights and distances, the most important thing to recognize is the relationship between the angle of depression and the angle of elevation. In most of the mathematical models we use in class, we assume a very helpful setup. First, the horizontal line at the observer's eye level is parallel to the horizontal ground. Second, the line of sight, which we discussed in the previous slide, acts as a transversal. This means it is a single straight line that intersects both of those parallel lines. Now, think back to your geometry lessons regarding parallel lines. When a transversal intersects 2 parallel lines, the alternate interior angles are equal. Because of this geometric property, we can conclude that the angle of depression from the observer looking down at the object is always exactly equal to the angle of elevation from the object looking up at the observer. This is a huge advantage for us, because as you will see in our next slide, it allows us to move that angle down into our triangle on the ground, making the trigonometry much simpler to calculate. Real-world example. Take a look at this scenario. Imagine a security guard is stationed at the top of a watchtower that stands 20 meters high. While scanning the area, he spots a suspicious package sitting on the ground. The angle of depression from the guard's eye level down to the package is 45 degrees. Our task is to determine exactly how far the package is from the base or the foot of the tower. To solve this, we will follow a structured, step-by-step approach. In step 1, we need to identify the information we already know from the problem statement. First, we have the height of the tower, which represents the side opposite to our angle, and that is 20 meters. Second, we have our angle of depression, which is 45 degrees. Now, for step 2, we apply the geometric principle we discussed in the previous slide. Remember how we learned that the angle of depression is equal to the angle of elevation due to the property of alternate interior angles. Since our angle of depression is 45 degrees, we can conclude that the angle of elevation from the package up to the top of the tower is also 45 degrees. This is a crucial step because it allows us to place our angle inside the right-angled triangle on the ground, making it much easier to use trigonometry in the next steps. Now that we have established the theoretical foundation and the geometric relationship between depression and elevation, let's put this theory into practice with a real-world application. Real-world example continued. Now that we have identified our known height and established that our angle of elevation is 45 degrees, let's move on to step 3, where we need to select the appropriate trigonometric ratio to solve this problem. Take a look at the triangle we are working with. We already know the height of the tower, which represents the side opposite to our angle. What we are looking for is the distance from the foot of the tower to the package, which is the side adjacent to our angle. Since we are dealing with the opposite and the adjacent sides, the tangent ratio is our best tool here. As a reminder, tangent theta equals the opposite side divided by the adjacent side. Moving on to step 4, we simply substitute the specific values from our scenario into this formula. We replace theta with our angle of 45 degrees, and we replace the opposite side with our known height of 20 meters. This gives us the equation: tangent of 45 degrees equals 20 divided by the distance. In the next slide, we will see how we use the value of tangent of 45 degrees to find our final answer. Real-world example, conclusion. Now that we have our equation set up, let's move on to step 5, where we solve for that unknown distance. Recall from our previous step that we have tangent of 45 degrees equals 20 divided by distance. Now, one of the most helpful values to memorize in trigonometry is the tangent of 45 degrees, which is exactly equal to 1. So, when we substitute that into our equation, it simplifies beautifully. 1 equals 20 divided by distance. To isolate the distance, we can simply multiply both sides by the distance, which leaves us with distance equals 20 meters. And there is our final answer. To conclude this problem, we can state clearly that the package is located 20 meters away from the foot of the tower. Before we wrap up this lesson, I want to point out a few common pitfalls students often encounter, so pay close attention to the next slide. Common mistakes to avoid. First, let's talk about placing the angle inside the triangle. This is perhaps the most frequent error I see in exams. Many students mistakenly place the angle of depression inside the right-angled triangle, specifically between the vertical tower and the line of sight. Please remember what we discussed in slide 2. The angle of depression is measured from the horizontal line looking outwards, not from the vertical structure itself. If you place it inside the triangle at the top, your entire calculation will be incorrect. Secondly, be careful not to confuse depression with elevation. It sounds simple, but in the heat of a timed exam, it's easy to swap them. Just keep this mental rule in mind. Depression always implies the observer is looking down from a higher point, whereas elevation implies looking up from a lower point. Finally, do not ignore the horizontal line. When you are sketching your diagrams, never skip drawing that imaginary horizontal line at the observer's eye level. As we saw in our geometric relationship slide, that horizontal line is the foundation for identifying your alternate interior angles. Without it, you won't be able to correctly transition your angle of depression into an angle of elevation. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the concept, it is very easy to make a small mistake that leads to the wrong answer. Keep these tips in mind, and you'll find these problems much more manageable. Let's move on to our final summary of the key takeaways. Key takeaways. First, let's revisit the definition. Remember, the angle of depression is specifically the angle formed between that imaginary horizontal line, the one where you are looking straight ahead, and your line of sight when you are looking downwards at an object. Second, regarding position, always keep in mind that for an angle of depression to exist, the observer must be at a higher elevation than the object being viewed. If you are on the ground looking up, that's a different concept entirely. Third, this is perhaps the most important mathematical shortcut we learned. The angle of depression is equal to the angle of elevation. This happens because the horizontal line at the observer's eye level and the ground are parallel, making the line of sight a transversal. This creates alternate interior angles, which are always equal. Finally, when it comes to application, here is my best advice for your exams. When you encounter a problem with an angle of depression, your first step should usually be to convert it into an angle of elevation. By doing this, you can easily form a right-angled triangle on the ground, which allows you to use your trigonometric ratios, like tangent, to solve for the unknown distance or height. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear before we wrap up. If you can master these 4 points, you'll be well prepared to tackle any problem involving heights and distances. Great job today.